Hello everyone. So previously in this first part of this video, we have discussed about the coordinate system, how to choose the right coordinate system. So today in this video, we will going to discuss about the vector calculus and their applications. So first we need to differentiate between the scalar and vectors. As we already know that the vector has some directions, but the scalar has some magnitude only, and for vector it is magnitude plus direction. So for example of scalar quantity, voltage, energy, time. But for vector quantity, in our case or in this particular subject, electric field intensity, magnetic field intensity, and sometimes the force, acceleration, these are all the vectors quantity. Now how to define a vector quantity? This is the case of a rectangular coordinate system, or a vector capital A is defined as a capital A suffix x. That here you can find that this ax is the magnitude quantity, and this small ax, which is the unit vector, it is showing the direction of the vector. Similarly, along the y directions, this is the magnitude and this is the direction of the vector, and for z direction, this one. So the total magnitude, we take mod of a, which is square root of the summation of this all magnitude, and the direction vector, which is the actual vector divided with the magnitude of that vector. These are fundamental things. Hope the class 12 students or the first year undergraduates already know these things. The types of vector in EM, that we consider position vectors, which is defines that the relative locations of the any point. Unit vector, field vector for E and H field, means electric field or magnetic field intensity, these are also used. Surface normal, that we sometimes consider one vector which is normal to the surface, and we define it as a suffix n, which is normal to the any surface. A line elements, dl, we sometimes we use the dl here, a small section of a line. Vector fields, we define mathematically defined as possessing both magnitude and direction at any locations in space. Fundamentally, we used EM theory. Mainly we used electric field, which is volt per meter, and the magnetic field, which is ampere per meter. These are all field intensity. Another thing is that electric flux density and magnetic flux density, which is defined as D and B. Visualization of the vector field lines is important, that we can understand the how vector is operating, and this is the core of the electromagnetics. So if we know understand the vector, then we can understand the electromagnetic field better way. So the key concept is here is that vector field allow us to describe how forces are transmitted through space locally and continuously. Okay. Physical meaning of the vector, electric field, magnetic field already been discussed. In energy storage, we use also vector uh, fields, and in wave propagation, time varying fields, we also use vector fields. Now here the core concept is that fields are not abstract matter, they are physically entities carrying energy and momentum. Okay, so whenever we discussing or mentioning the field, electric field and magnetic, mostly we deal with these two things in this subject. So means electric energy or magnetic energy is transmitted through a space, through a medium, and that is all about that electric field or magnetic field, or the vector fields of electric and magnetic. Now fields are different types of fields are there. That is vector calculus is related to different types of calculations, that is variations, gradient, divergence, and curl. So why we require to understand that em quantities like e and h are not constant, they are changing with respect to their positions. And vector calculus provides a tool. These methods are tools to allow to quantify this physical behavior. Mathematically, we define these physical phenomena. One is gradient, another is divergence, another is curl. So this is the Dale operator, which is known as the nebula, and it applies to the scalars and vector quantities to find the gradient, divergence, and curl. So for scalar quantities, we use del v, that is known as the gradient. For divergence, del dot a, which is known as the dot product, and for curl, del cross a, which is known as the cross product. So del dot a and del cross a, dot product, cross product is basically the dot product defines the two vector along with the cosine angle between them, and the cross product is the two vectors along with the sine angle between them, and the direction of the vector will be the normal to the surface of that vector. So that is not mentioned here. Now the gradient is applied on the scalar field which produces a vector field. So here v is a scalar quantity. If we apply over v, the result is the vector quantity. So the relationship between electric field and the electric potential is the one of the major important application of the gradient. So physical meaning, what we can say, the gradient vector represents the magnitude and the direction of the maximum spatial rate increase of the scalar field. Now the divergence. The divergence is applied over a vector field which is denoted as del dot a. So divergence is basically defined as the uh, vector from outward towards any point. So this in this figure you can see that this is a flux diverging, which is known as positive divergence and also known as source, and negative divergence is sink, where flux is going towards the point. So whenever there is no divergence, we call it as a solenoidal field. So here the result will be the scalar quantity. Now divergence of any vector field intensity, that is the d is the electric flux density, which is related to the volume charge density. So that is where we apply the divergence. So this is one of the Maxwell equations, which is known as the Gauss's law. Now the Karl operator, the physical concept or physical meaning is that it is rotation or swelling. It is denoted as del cross a, and here the result is vector. We apply it over a vector and the result is also a vector. One simple example, the paddle wheel analogy is there, that if you place a tiny paddle wheel in the field, the Karl describes the axis it rotates around and how fast it spins. Okay, so from this figure you can understand this one. So Karl in EM field also we apply the Karl of E, and which results the change in the magnetic field. So this is very important equations, and it is known as also Faraday's law, that whenever we are taking the Karl or the change in the electric field along any circular path, which results the change in the magnetic field. So del B del T is basically denoting the change in the magnetic field or time varying magnetic field. So this is the summary of the operators, the gradient, divergence and curl, the notations, the transformations. That's gradient is scalar to vector, divergence is vector to scalar, and curl is vector to vector. The meaning is maximum rate of change, that is gradient, either source or sink density, and this is the circulations or rotations. And the relationship with gradient is the potential of field. This is the Gauss's law for divergence, and the curl, that is Faraday's law. There are some other application of or operations of the vector calculus. One is line integral, one is surface integral, and another is volume integral. So line integral is applied any path or curve, surface integral is applied over any 2D surface, and volume integral is applied over any enclosed volume. Or and sometimes we physically work or voltage we define it through line, the electric flux through define any surface, and the stored energy is defined inside any volume. Some of the important theorems related to the vector calculus are that Gauss's divergence theorem, which defines that the surface integral through any closed surface is equals to the volume integral of that vector, uh, that is the volume enclosing that surface. So closed surface is basically defines the volume. Therefore, that surface integral is equivalent to the volume integral. That is the Gauss divergence theorem. And another is the Stokes theorem, that the line integral over any closed line is equivalent to the surface integral. So the here in both the cases uh, we can see the integral notations of the two theorems, and these two theorems are always applied in solving various electromagnetic problems. So you have to remember these two theorems, and you have to apply quite often whenever we going to solve numerous problems. Now, how it is connected, as already mentioned, that del dot D equals to rho V. It is the very much well-known Gauss's law. Del dot V equals to 0. We know that the magnetic field lines cannot be separated. Therefore, through any through any surface, the number of field lines going into the surface is equivalent to the number of field lines going out of the surface. So that's why that del dot B equals to 0, or magnetic field lines cannot be separable. We already know. This is the Faraday's law, and this is the modified Ampere's law, where Ampere, which is done by the Maxwell, that Maxwell proposed that there will be some change in the electric field intensity, or sorry, electric flux density with respect to time whenever we going to um, solve, or there is any magnetic field. So that change in the magnetic field not only change in the current, it also changing the electric flux density, means change in the electric field. So whatever we studied, which is there are some connection with the Maxwell equations, that coordinate system of for structures, vector fields for quantities, and vector calculus of different behaviors. So finally, how it will help you? This will help to solve various problems related to the transmission lines, related to the antenna, related to the any RF or microwave circuit problem. So boundary conditions, characteristic impedance, wave propagations, voltage and current distributions. So the connection is that the bridging the gap between Maxwell equations and the circuit theory. So finally, concluding remarks for this prerequisite electromagnetic theory um, videos. There are these two videos. Earlier we have discussed in coordinate system, and this one is the next part. So this prerequisite is very much important to understand that electromagnetic theory for the undergraduate students, and it will. I hope this will help you to come out from your fear that EM theory is not like that things, that it is very complex things. No, not at all. If you know mathematics, it will be very easy for you. That's so the main conclusion remarks is the mathematical foundation. So geometry simplifies the physics. So if we know the geometry, then we can apply physics properly. Calculus describes the behavior. So if we need to apply or calculate the behavior, then we have to apply the calculus. And the abstract Maxwell equation is always need to know everybody for understanding the electromagnetic theory in better way. So in the right hand side, the philosophy is that EM theory is physics, mathematics, and visualizations. So visualizations is a bit difficult, but physics and mathematics are very simple to everybody. Those who have doing undergraduate in electronics and communication engineer or allied fields where they have to study electromagnetic theory. So thank you everyone for your valuable time.